So hi everyone to the last day of our talks, and I do apologize for this, for changing the program, and thank you very much, Vera, for agreeing to give the talk. So our next speaker is Vera Seganova from University of California, and she's going to speak about generalized Kac-Moody subalgebras and groupoids.
Okay, thank you very much. I'm very pleased to talk in honor of Robert Moody, who I never met, but who I knew, of course, because probably these formulas, which I'm going to write down, I know practically when I became a student, and I'm going to talk about some generalizations of Kac-Moody algebras. So if we start with the matrix, square matrix satisfying certain conditions, let me write them down. So off diagonal elements are non-positive integers. You have 2's on diagonal, and you have something which one can call weak symmetricity, that the symmetric entries above 0, above non-zero. When you can try to build a Lie algebra, GM of A, and I made this notation, I explain in a moment why, but this is in honor of Robert Moody here. And so what is it? It's so the size of the matrix is n by n. We have these generators, and we have very famous relations, which I'm going to divide into groups. So this first group, I'm going to denote the star, and I will also refer to them as a Chevalier relation. And then there's second type of relations, which I'm going to refer. I'm not completely sure that it is correct historically, but I'm going to refer to them as Serre's relations. Namely, okay, and historically, I think that first was coming from classification of finite dimension simple algebras, so they can be given by such set of relations. And I think in his PhD thesis, Professor Moody actually solved the problem of classifying matrices satisfying certain conditions. Somehow, exactly at the same time, Katz also address the same problem. That's why these algebras I'm talking about are called Kac-Moody algebras. And of course, the simplest example is just finite dimensional simple Lie algebras. And so this is the definition 1. And I'm going to give now the definition 2, as it is given in the book of Katz. So I'm going to call this algebra GK of A, or the conditions are the same, but instead of doing, we consider this relation a little bit technicality. There is a little bit of technicality. If your matrix is degenerate, then you have to add certain elements in your Cartan algebra, but you're going to take the same Chevalier relations, but instead of considering Serre's relation, what you can do, you can construct a big algebra, G trivial of A, which is just satisfying Chevalier relation and quotiented by the ideal R, where one can show that R is maximal ideal intersecting H trivially intersecting the Cartan subalgebra H trivially. And the first question one can ask if these two definitions are equivalent, and the same cuts proved that they are equivalent. And these algebra are isomorphic if the Cartan matrix is so-called symmetrizable. Which means by it is proof of Gaber. Thank you. Right, you're absolutely right. I just forgot. Of course, yes. So Gaber and Kac prove that these two give you the same algebra if the matrix is symmetrizable. What does it mean that it is symmetrizable? You can multiply it by diagonal matrix and make it symmetric. So you multiply by some diagonal matrix. And then it becomes a symmetric matrix. And also this condition is equivalent to the existence of an invariant form on this algebra. And it is surprising, in general, it is not known. If it is true, it's still open. If A is not symmetrizable. So what I'm going to talk about. So later on, there were certain generalization of these constructions. In particular, in principle, we can forget about these conditions which are written on the top of this board and try to construct the algebra and see what you can get in this way. And there are two important cases which are generalization. One, of course, is very famous by my colleague from Berkeley, Richard Borchers, who allows zeros on diagonal. I'm not going to give a definition because I'm mostly not used. And he was solving this famous problem about moonshine and monster group using these generalized Kac-Moody algebras, how he called them. And another thing, and that's mostly where I'm coming into the picture, is so-called superalgebras. And I don't know, since I'm talking in the audience, which might not be completely in this business. So those Lie superalgebras are there something which has a Z2 grading. And they have graded identities. So what here, bar means just the grading. So all identities are written for homogeneous elements. and then a Jacobi, which I will write in this form. Is it visible or I need more? Okay. So I'm writing down that this is a derivation, and the main rule in all this game is when you switch to variables, you add something like the sign. So the story is the following, that several people were working on classification of simple superalgebras over complex numbers. By the way, I'm going to work over complex numbers all the time. So there was some work of Kaplansky and Hochschild, and finally Katz in 1977 published the complete result, which was classification of finely dimensional simple Lie superalgebras. And it was actually quite a nice list. And in this list, a very important part, take Kac-Moody Lie superalgebras, finely dimensional, of course. And then immediately, if you start working with these superalgebras, you will notice two new things comparing to this thing, to this definition over there. And the first thing is, but of course now zeros are allowed on the diagonal. Possible, like in the Borges algebras. And second, even more interesting thing, which doesn't happen in the usual case, is that several differently looking Cartan matrices can give you the same object, the same superalgebra. So define isomorphic superalgebra. And here I would like to talk about one example when it happens, the simplest example when it happens. So this is the Lie superalgebra SL12. So how you can think about it, it is matrices, block matrices, 1, 2, 1, 2. I'm trying to do it the most easiest way. Okay, so those are matrices with even part. So maybe I just write down the diagonal thing, the super trace. 0 means that A minus B minus, oh, sorry, yeah, A minus B minus C 0. So the matrices of this form where this is the even part. And this is the odd part. Okay. And what I would like to do, I would like to find the Chevalier generators there, where the Cartan has a rank 2 in this case. And the Chevalier generators are going to be two different ways. So what you can do, basically, you have to define what is called the Borel subalgebra. And the Borel subalgebra means a triangular subalgebra. But the point is that you can order the basis in this basic space where it works. And so you can take, for example, like here, I'm going just to mark. So the matrix here is going to play the role of E1, and the one here is going to play the role of E2. And then the Cartan matrix is going to look like this. And then what you could do instead, you can do this. There's more, but I just want to show you example. I'm going to talk later maybe about this example more. Okay, and the matrix is going to look like this. It could be -1, it could be +1. You see, there is a trouble here. This is one of the troubles here. Then you cannot normalize because it's pretty clear that you can multiply any generator hi by some constant lambda I, and that gives you the different, the same algebra, right? And since if we want here 2, well, because we want SL2 secretly, right? Then, but here you can put -1 as well. Yeah. Okay. It doesn't really matter so much. And you can do one more thing of this. And what does it really mean? That here, not all Borel subalgebras are conjugate. And this is very important. This whole business of super geometry. For example, you have many plug manifolds which are different. So in that sense, while group somehow seems not enough in this setting. So while group, which plays very important role, I cannot move any to, I cannot relate any to set of generators by the while group. And what you have to do to introduce some notion of the groupoid, which I'm going to talk about. So this is the main topic of, so I would like to define quite general. So there are 2 ideas there, which I try to explain, but probably at this moment I should tell that I work on this. Actually, we finished this. I just didn't post it yet with Marie Gorelik and Vladimir Kinich. These are my collaborators on this project. And since now it's going to be a little bit technical and I really need a definition, I would like to explain a little bit of motivation. Why do we bother about all this? So there are 2 main things. First, even in the classical situation, using this groupoid approach, you can recover Serre relations from Chevalier relations. And second thing is that you actually cannot, without this approach, you actually even not get all the necessary relations in super case. So to get relations in super case, you need this approach. You need analog of while group. And finally, and this is also kind of the remark, we certainly in the super world, we certainly see the example when Katz is not equal to Moody, if I can say so. And pretty simple example. we still don't know. Well, either the classical situation. Oh. But one of the things here that I actually don't want to write A anymore because I have several A's and I should remember this as well. So now I'm going to define the main object of my talk. And as I said, it's going to be a little bit technical. So for people who, by some reason, forgot what is a groupoid, it is a very simple thing. It is a category where all arrows, all maps are invertible. Okay, so I'm going to erase now this part. Okay, so we're going to fix. So now I'm going to give rather technical definition. So we start with a fixing finite set. And we are going to define the category. So we're going to define the set of objects and the set of arrows between them. And so first of all, we consider, so what is our object? So here we have few things. We have H, which is a vector space. We have two maps, A and B, and we have the parity map P. This is all decorations which I need in this case. So A is just a map of X to H. So you should think about X as a set of indices. B. So this gives me what's so-called co-roots. That gives me roots. And then I also have the map, the parity map. Since I'm working in the super situation, I have to remember if my generator even or odd, but I should remember always that in this approach, Cartan subalgebras consist only of even elements. So this is a Z2 grading on the set of generators. So arrows. There are three types of arrows. Reflections, and I'm going to talk about them a little bit later. So reflections do not change H, but do change all the other characteristics. Since it's the most important thing, I'm going to give the definition of reflection after I formulate all three errors. The second errors are so-called tautological errors. So if I have H and H prime and an isomorphism of vector spaces, just linear isomorphism of vector spaces, and when I construct A prime as composition of vector A and B prime as a du1, and P prime is equal to P, homotety so what is this? I'm basically allowing now, I have lambda from X to C star, and this is a rescaling of A prime, so A prime of X equals lambda of X times A of X, and B prime of X remain as they are, and P prime is. Okay, so here I change, also H doesn't change in this case. And this is exactly related to the fact that I can actually rescale my Cartan matrix by multiplying on the diagonal matrix, and that doesn't change the situation. Now I'm going to explain what are reflections. And it's also a little bit long, but then I hope that would be it. I actually have to like formulas. So there are two types of reflections. Isotropic reflections which occur if so reflection are all by the index set Rx, and isotropic, anisotropic first. No, maybe, yeah, let us do anisotropic. Because this is a sort of usual reflection. It happens if AXX is not 0, and when we need the condition to AYX, sorry, AXY, excuse me, AXX is negative. Integer if P of X is 0, this is the parity of the generator, and it is this one. So some indices are not reflectable. We cannot make a reflection of all indices in this generality if P of X is 1. And then let me write down here. So the formulas for this anisotropic reflection are pretty simple. And something which you know how it works with the while group. Okay, and then we have isotropic. Yes, H prime equals H. And the parity function is preserved. So this is happening if I have 0 on the diagonal. And then I have so I remind you that I do have an arrow between H, A, B, P and H prime, A prime, B prime, P prime. And so there's formulas which are all quite involved, but they come from experience, and I'll explain in a moment why we get these formulas. I'm just writing them down so they sit here. So first thing, what happens if the index X is the same as Y? We do not change anything for Y if X is not equal to y and axy is 0. So of course, the most interesting case is that x is not equal to y, and a of xy isn't 0. And here what we get, make a little bit more space. So this is A prime, and for B prime, I have just the sum. And for P prime, I shift it by 1. And I am afraid that I really didn't explain what is AXY, but this is, of course, a Cartan matrix. So AXY is a result of pairing A of X and B, where this is the nature of pairing between spaces. And this is basically Cartan matrix. So you might ask why such a difficult formula happens here, and why do I know that this is the right formula? For this, let us look, why do we know the formula over there? And actually, this formula over there is the result of the fact that if I have 1 by 1 matrix with 2 on diagonal, this is SL2 representation theory. Right, and what we're doing, we know that the representations of SL2 are given in strings, and you go from one string to another. So if my generator is odd, but it's still anisotropic, and it has 2 on the diagonal, there is the little superalgebra OSP12, which also has a very beautiful representation theory, and that gives us formula. And then there is a third algebra, which is called SL11, which corresponds to the situation when I have 0. So here and here, I have Cartan matrix 2, but parity here is 0, and parity here is 1. And here I have a parity 1. And the representation theory of this is terribly simple, basically reducible representation theory. You either have something of dimension 2, which corresponds to this K, or just dimension 1, and you do not have any other irreducible representations for this algebra. So what is this algebra? It is sort of analog of the Heisenberg algebra in the super case. So let me just write it down by the way. H, and H is in the center. So now I defined the category, I defined the morphisms between objects. And I would like actually, so this is a little bit by generators and relations. I define the error, but I should now say when 2 errors are equivalent. And the 2 errors are equivalent if, so gamma. So I call objects by V, gamma, V prime, and delta are equivalent if they induce the same morphism on spaces, on the space H, if gamma and delta induce isomorphism on H. Now, what I can do with it? Well, I can define a few things. So first of all, I have something pretty huge. And it is also not connected, of course. So I have to pick up a connected component. Connected means I take the objects which are all isomorphic, right? There are errors between them. So for every so every connected component I'm going to call root groupoid. This is a definition. So what I would like to now is to define the algebra. So I'm going to define the algebra supported by the root groupoid. Root algebra G. So, and since I'm already very technical, and maybe I should stop now writing down the formulas, but I really don't know how to make this talk about writing any formulas. So the point is, for every V in my groupoid, I'm going to define this algebra G twiddle V as in the definition of Katz. And this is, I'm not going to write down it again, but this is the algebra defined by Chevalier relations. And then I'm going to consider, so what is pretty clear, and when I do the reflection, it doesn't induce an isomorphism between two Chevalier algebras. But what I can do now, I would say that G is supported on R naught. If I have a surjection for each V, okay, and so this is a surjection. Injection on H, restriction to H is injection. And it is consistent with the groupoid. Picture, so. And so on the generators, if I have gamma, the morphism from V to V prime, this induces an isomorphism here. So I actually can put, so this is the same algebra G, but it's a different set of generators. And I want to have the isomorphism here corresponding to this gamma. Okay. And in principle, such algebra couldn't even exist. I mean, it could be only trivial one. So we call groupoid admissible if such algebra exists. R0 is admissible. there exists a root algebra. So we can actually say exactly when such algebras exist, when groupoids are admissible. So R0 is admissible. If and only if, for every reflectable version, every reflectable index at every v, so for every v, there is no top arrow. There is no top arrow. There are arrows in both directions, but they are not isomorphism. Yeah. So there is no top arrow. But here you see, since I know, I can if I have a so in principle I do have arrows here, but they are not an isomorphism. And so in a way, I would like to take to look at the algebra such that it is. So R0 is admissible if at any element here and any invertible x, we have weak symmetricity x, y equals 0 if and only if a, y, x equals 0. So we can prove it only in this case. Only in this case, the groupoid is admissible. So now I probably should move very quickly to explain what else we did without technical details. But maybe with one, I actually would like to check how much time I have. When did I start?
18 minutes.
Okay, good. Then I think I can give you an example. I would like to explain something which is called a skeleton, which is actually the combinatorial graph behind this. Skeleton is something when you only allow reflections. And then if you are in a finite dimensional situation, if your root algebra is actually finite dimensional, when your skeleton is essentially some finite graph. So let me go back to this example of SL12. Although the skeleton here, so here I have X consists of two elements, X and Y. And I would like to, so in the skeleton, I have 6 vertices. And you actually recognize them. They look a little bit like SL3 picture. But the only thing is that I do not know how to go this way. And I put the Cartan matrices as a vertex. So I assume that X is even and Y is what? So you see, I have two type of Cartan matrices in this case. But secretly, it is really 3. Okay. So the trick is that, of course, inside all this, I do have a while group as well, usual while group. I will explain in a moment. But in this case, the while group is not so interesting because it's just Z2, the cyclic group of order 2. And it acts on this skeleton, preserving the shape of the Cartan matrix, of course. So what I can do, first of all, as soon as I'm working with admissible groupoid, I have the root algebras. And in fact, we can prove how many we can have infinitely many root algebras in principle, corresponding to a given groupoid. But we have final object and initial object, and they are called accordingly Moody and Kac root algebras. So and this is a very easy statement. And when all root algebras supported or are not, we have GM and GK, and any root algebra G is a quotient of GM. And GK is a quotient of G. So another interesting thing, whenever I have a groupoid, and it is a connected groupoid, then I can talk about an automorphisms of the vertex of the groupoid, the group of. So if I have this R0, and I have P, line and R0, then I can ask about automorphism of R of V, and this is a group, and we can compute this group. And I don't want to spend time on it, but as I already explained, what I can do, I can construct a while group. Maybe I will explain in a moment how to construct a while group, but let me just tell you that the while group, generally speaking, is a subgroup here. There are cases when they coincide. For example, if it is classical Kac-Moody, but with non-degenerate Cartan matrix, when these two groups coincide, so then The while group at each vertex are also, of course, the same. But generally, even in Kac-Moody case, the automorphism group is a little bit bigger. Say for a fine Kac-Moody algebra, it's a little bit bigger. So general. Is the one group direct product of certain unipotent algebraic group. Okay. Fine. So it is C star in the case, or not C, C additive group of for a fine case, for example. Yes, so I can define roots, root lattice. And in principle, I can define it only at each vertex, so root lattice Q. So I really have a lattice here. It depends on the vertex, but they're all isomorphic, of course, because I have arrows between them. And this is just the span, the span of B of X. So just take, so, and therefore we actually have roots and root decomposition. And we have real roots and imaginary roots. So what are the real roots? So real roots, maybe so as I said, I do have an identification. So real roots, there's some gamma. So real roots are B prime of X, composition with gamma here. So it's basically what is happening. You do these reflections and you pick up the generators after you do several reflections. So those are real roots. They are free type, non-reflectable. So what could happen, for example, if you do this definition for the Borges algebra, when we have isotropic and when we have anisotropic. So, and basically, you take the reflections generated by all anisotropic roots. So W is a group, linear group. Subgroup in GL in GLH, generated by all anisotropic reflections. By reflections with anisotropic real roots. So, and since I was listening here about tilings, which I'm not know much about it, but what I realized, but I do have some tiling associated with this structure because I have the while chambers. So there is actually the while chambers. Which covers some convex set. But this styling is simplicial. Okay, so I do have something like, so there is also some nice property of this groupoid, which I call, you can say Coxeter property, which I cannot write down exactly like in the Coxeter group, but this is the property that I actually can define the length of on my set of objects in the groupoid. So very briefly, let me explain what is happening. So let me just give you one more example of just x and axx equals 0. And then let me just explain what is gk in this case. So the skeleton is actually consisting of two vertices here, because you have one reflectable root, but this is isotropic reflection. So the matrix are the same. Of course, the algebra, I have gk, and gk is generated by ex. Dimension of h is 2. Because I should say that the dimension of h is 2n minus rank of Cartan matrix. I have ex, fx, and ex, fx is fx. But this is a superalgebra, and therefore there is no reason why the commutator of ex with itself is not 0. So actually, GM is five-dimensional, so it has ex, the commutator with ex with itself, which is actually twice ex squared. But let me write it down this way. When I have a of x and one more element which gives me the grading, and I have also fx, and then if I so this is algebra here, but I can quotient by these two, and I'm going to get the algebra GL11, and this is GK. Okay. And this is, of course, a very simple example. It is related to the situation that the Cartan matrix is degenerate. So for example, if I go to SL12, it doesn't happen. But however, if I go to SL22, it happens again. It's more complicated, but it happens again, that I do not have the same algebras. And maybe in the last moment, I'm going to talk about classification. So there are certain results, except definitions, mostly of them were done before the definition. So, but maybe even before I do this, there are three types. As before, finite, affine, and indefinite. finite. So what I'm going to do, I'm going to take everything, the cone generated by so Q of V is R plus P of X, right? So I'm going to define Q plus as an intersection of, sorry. So let us call this Q plus of V. And when we take intersection over all vertices, and in the finite set, so here Q plus is 0, here Q plus is a line, R plus array rather, just one dimensional, and here none of above. So I first come up with this idea, although never did it technically in all detail, when I wanted to classify all finite order, finite growth. Finite growth. Kac-Moody Superalgebras. And then with my, at that time, graduate student, Crystal White. So we prove the following theorem. The algebra is a finite growth, KM algebra. What is finite growth, I should say? There is a natural gradient on the algebra, and you want your graded components, dimensions of graded component grow polynomially. So this KM algebra is finite growth. And we assume that the rank is greater or equal than 2. And I'm formulating it like this. Then R0, all real roots are reflectable. This is the first condition. I also assume that Cartan matrix is decomposable. The second thing is that it is of type finite or affine. So it's finite or affine. Okay, and then Crystal classified all affine. And I should say about previous results, because this classification is interesting in itself. So all finite dimensional are classified by Katz in 77, and they are all symmetrizable. Simple. All finite growth symmetrizable are classified by Van der Leur in his thesis, and I think it was 84. And they're coming from Katz by loop and twisted loop. So they are loop and twisted loop. Of finite dimension. But then Hoyt, I think in 2008, actually classified non-symmetrizable. And she get one series, which we call QM1. Oh, sorry, 2. So this is the following story. I might not have time to talk about it, but it is a twisted, the twisted algebra of another algebra, which is not Kac-Moody, but you still can twist it. This is algebra QN, people who know, and you can twist it. And then you get really Kac-Moody algebra, which is not symmetrizable. And one, which is kind of important for physicists because it's actually conformal. And this is a deformation of the loop algebra of SL12, which I explained to you here. Let me write down the Cartan matrix. So it depends on parameter B. We assume that B is not integer. And B1, B and B prime give the same algebra if they are different by integers. So it is interesting that here you really see the action of groupoid in changing this parameter B. Well, I think I should stop here. Thank you.